Hi friends, here I am going to present session 5 of paper 7 analysis 2 and algebra 4 of 6th semester mathematics. The topic is continuity and differentiability. So similar to the function of real variables, there also we can verify continuity and differentiability of real functions. So like that, here also we can find the continuity and differentiability of complex functions of complex variable. So let us see the definition. So the definition is similar to the real function. So the definition of limit continuity is we express continuity, we find continuity in terms of limits. So a function f of z is said to be continuous at a point z dot if the function f of z is defined at z dot. So it is similar to the real function. F of x is defined at x is equal to a. And second condition, limit of f of z as z tends to z dot exists, and that limit is equal to f of z naught. So that is the third condition. So it is similar to, it is same as the case of real functions. So here a function f of z is continuous in a domain D if it is continuous at all points of D. Now we have to solve some problems on this. Example 1, show that the function f of z is equal to z square plus 2z is continuous at z is equal to I, at a point z is equal to I. So first we have to find f of I. So f of I is equal to minus 1 plus 2i. Replace z by I, we get minus 1 plus 2i, and then we have to find the limit of z square plus 2z as z tends to I. So here also we replace z by I, we get minus 1 plus 2i. So here the limit is same as f of I, therefore the third condition is satisfied, hence the given function is continuous at z is equal to I. Second example, show that the function f of z is equal to z square divided by z to the power 4 plus z square plus 1 is continuous at z is equal to e to the power I pi by 4. So at the point e to the power I pi by 4, so you have to find f of e to the power I pi by 4, that is equal to 1. Replacing z by e to the power I pi by 4 and applying Euler's formula, we get that is equal to 1, and finding the limit. So the limit is also 1. So here the limit is equal to f of e to the power I pi by 4, hence the given function is continuous at z is equal to e to the power I pi by 4. Let us see the example number 3. So here we have to examine whether the function f of z is equal to z bar by z is continuous at z is equal to 0. Here z is equal to x plus iy. So f of z is z bar by z, that is x minus iy by x plus iy. So here we consider two cases along real axis, along x axis y is equal to 0. So the limit of f of z is plus 1, y is equal to 0, we have x by x, that is 1. Along y axis, imaginary axis, x coordinate is equal to 0. So the limit of z bar by z is equal to minus iy by iy, that is minus 1. So here the limits are not same. So limits are different. The limit of f of z does not exist. Hence the function is not continuous at z is equal to 0. Next we have to see the differentiability of function of complex variable. So as we define in real function, here also we have the same formula. A function f of z is said to be differentiable at a point z is equal to z naught if the limit of f of z minus f of z naught by z minus z naught as z tends to z naught exists. So if this limits exist and this limit is called the derivative of f of z at z is equal to z naught, and it is denoted by f dash of z naught. So it is similar to the real function. There we have to denote f dash of a, that is f of x minus f of a divided by x minus a. Same definition. So here we can define this derivative using delta functions, delta z, delta x, delta y. So if delta z is equal to z minus z naught, then f dash of z is equal to Just we substitute z as delta plus delta z. F of z plus delta z minus f of z divided by delta z, as delta z tends to 0. So this is also the derivative of z, f dash of z, derivative of f of z with respect to z, f dash of z. Let us see some examples on differentiability. Find the derivative of f of z is equal to z cube at z is equal to z naught. So as we know, the differentiation of x cube is 3x square. So here also the differentiation of z cube is 3z square. So at z is equal to z naught, it becomes 3z naught square. So let us, we have to find by using the definition, f dash of z naught is equal to limit of f of z minus f of z naught divided by z minus z naught. Substitute f of z and f of z naught, we have z cube minus z naught. So it is a cube minus b cube. A cube minus b cube is a minus b into a square plus ab plus b square. So z minus z naught cancel. After substituting, after applying the limits, we get 3z naught square. So this is the derivative of z cube at z naught. Let us see one more example. Find the derivative of f of z is equal to z minus 1 by z plus 1 at z is equal to 2 minus I. So you have to find f of 2 minus I. F of 2 minus I is 1 minus I by 3 minus I. So f dash of 2 minus I is equal to, same by definition, according to definition, limit of f of z minus f of z naught, f of 2 minus I divided by z minus 2 plus I, as z tends to 2 plus I. We get, after substituting f of z and f of 2 minus I, we get this one. So as z tends to 2 minus I, this is the, after multiplications we get 2z minus 4 plus 2i. So if we directly substitute z tends to 2 minus I, substitute z is equal to 2 minus I, we get this one. We get 1 by 25. 1 by, here we have to remove this z minus 2 plus I, because if you substitute 2 minus I, we get 0 by 0 form. So you have to remove this factor. You have to remove the factor z minus 2 plus I in numerator and denominator. So we get 2 by z plus 1, 3 minus I. After substituting the limit, we get 1 by 25 into 4 plus 3i. So this is the derivative of f of z at z is equal to 2 minus I. So here we have one theorem that is related to differentiability and continuity. So as in the case of real functions, every differentiable function is continuous, but the converse is not true. Same in the complex function also. If f of z is differentiable at z is equal to z naught, then f of z is continuous at z is equal to z naught. So by data, f of z is differentiable at z is equal to z naught. So by definition, we write the derivative. F dash of z naught is equal to limit of f of z minus f of z naught divided by z minus z naught. This limit exists and it is unique. So next we have to consider, we have to show that f of z is continuous. So to prove it is continuous, we have to find the limit of f of z as z tends to z naught. That limit is equal to f of z naught. So for that we consider limit of f of z minus f of z naught. We take RHS into LHS, and we have to use the definition of differentiability. So for that we have to multiply and divide by z minus z naught. So this limit becomes f dash of z naught, and this limit is z naught minus z naught 0. So we get limit of f of z minus f of z naught is equal to 0. So that implies limit of f of z as z tends to z naught is equal to f of z naught. Here f of z naught is a constant, so this limit is same, f of z naught. Hence, so this is nothing but the definition of continuity. Hence f of z is continuous at z is equal to z naught. So every differentiable function is continuous, but the converse is not true. That is, every continuous function need not be differentiable. So let us, we have to justify this statement by giving an example. For example, f of z is equal to z bar. So which is continuous at every z. but not differentiable. So z means it is x plus iy, z bar is x minus iy. So along x axis y is equal to 0, the limit of z bar, that is limit of x, is equal to 0. Along y axis x is equal to 0, so limit of z bar, that is limit of iy, that is 0. So here the limits are same, the function is continuous at z is equal to 0. Now we have to find f dash of z. So f dash of z is equal to limit as delta z tends to 0, f of z plus delta z minus f of z divided by delta z. So you have to substitute f of z plus delta z as z bar. So it is conjugate of z plus delta z minus z bar by delta z. Substitute z as x plus iy, delta z as delta x plus I delta y. So after simplifications, we get f dash of z is equal to limit as delta z tends to 0, delta x minus I delta y divided by delta x plus I delta y. So here also we consider two cases. If delta z is real, then imaginary part delta y is equal to 0. Here f dash of z is equal to limit delta x by delta x, that is 1. If delta z is imaginary, then delta x is equal to 0, real part is equal to 0, and f dash of z is limit of minus I delta y, I cancel, so I delta y by I delta y. So this limit is equal to minus 1. So here the limit is along real axis it is 1, along imaginary axis the limit is minus 1. So limits are not equal, it's not unique. The derivative f dash of z does not exist. So the function is not differentiable. F of z is equal to z bar is continuous but not differentiable. So a very continuous function need not be differentiable. So these are the things very important related to continuity and differentiability. Thank you.